Okay, this is lecture 14 of basic calculus 1. Recall that we had discussed about the differentiability and the derivative of a function in our last lecture. So, today we will be talking something about derivatives and tangents. Physically, you see that the derivative is the speed, instantaneous speed, but mathematically it has something to do with the tangent. So, first we will discuss what do we mean by a tangent to a curve. Let us say the curve which is in blue here, that is our curve, and we consider a point say x0 on the x axis, corresponding to we have a point on the curve which we write as p, coordinates as x0 and f of x0. At that point we feel that this pink line, straight line, is the tangent to the curve. So, intuitively it means it is a straight line, it is a unique straight line which touches the curve at that point. That is what we intuitively feel that a tangent should be. So, but there are some critical cases. So, taking that into account, we may think of a tangent to a curve as a cryptical description. It is a unique straight line that has exactly one point in common with the curve at identically 2 points. So, that is the critical matter here. What do I mean by identically 2 points? So, it would mean something like if you take the tangent, it is a unique straight line, and what sort of straight line is it? If you change its slope a little bit, then it has more than one point in common with the curve. That is what it means. It is a curve, touches the curve at identically 2 points. If you change a little bit in its slope, the direction, then there will be at least 2 points common to the curve. It will become a secant. So, that is what we feel a tangent is. But this is about the curve in the plane. We are only talking of curves which are functions, and specifically y equal to f of x. For that we want to see what will be the tangent at a point. So, as you see, for us the definition will be something like you take 2 points on the curve, say p and q. Let us say the distance corresponding to that in the x axis is h. So, one is at x0, another is at x0 plus h. Now, we have 2 points p and q. P coordinates as x0 and f of x0, q has coordinates x0 plus h and f of x0 plus h. H could be negative, the other side. So, q could have been here on the left of p. So, we allow that. We write x0 plus h, it does not mean h is positive always. So, now we have the secant, the straight line joining these 2 points p and q. So, our feeling is that when h goes to 0, this secant becomes a tangent. So, that will be our use of the notion of tangent here for a curve. Okay, suppose y equal to f of x is the curve and we take 2 points p and q, then you join these 2 points to get the secant. And what is the slope of the secant? It is y2 minus y1 by x2 minus x1, which is for q and p f of x0 plus h minus f of x0 divided by x0 plus h minus x0, which simplifies, the denominator simplifies to h. So, you get this ratio, increment in f divided by increment in x. So, our aim is when h goes to 0, this will be the slope of the tangent y equal to f x at the point x equal to x0. So, this is exactly the definition of derivative. When limit goes to 0, the right hand side, that is the derivative at x0. Therefore, we would say that f prime x0 is the slope of the tangent to the curve y equal to f of x at x equal to x0. So, this is when everything goes well. There can be some cases where this fails, like when the limit does not exist, for example. or it blows up, becomes infinity. That is also one of the cases of the non-existence. So, when it blows up, what happens? Slope becomes infinity, means the straight line which we get from this, whose slope is it, that is having angle with x axis as phi by 2. So, that means a vertical tangent. So, that is the case which is not here in the differentiability. So, for a vertical tangent, this will fail and its slope is not defined. If you take the slope in this way, the definition, then it will not be defined. So, you have to take that into consideration while considering tangents. So, differentiation means it has some more constraints than just having an existence of a tangent. So, in general, we will stick to this view of a tangent, and here we are taking a curve, not necessarily y equal to f x as the curve. So, there you might be able to express y as a function of x or x is a function of y. For example, your semicircle, the vertical one, right, the right side. If you take this one, this is x equal to f of y is the function, not y equal to f x. Y equal to f x is not a function because a vertical line can cross it in 2 points. Okay, so, we are considering both dy by dx and dx by dy. If they do not exist at a point, then a tangent to the curve is not defined at that point. So, that is obvious from this, and if both of them are 0 at a point, then also a tangent to the curve is not defined at that point, as we have seen for the vertical tangent y equal to f of x. If at least one of these two, dx by dy or dy by dx, they exist and it is a non-zero real number at a point, then a tangent to the curve exists at that point. So, since we are considering y equal to f x, our dx by dy goes away, we just concentrate on this, that dy by dx is a non-zero real number. That would give rise to a tangent. Of course, it will exclude the vertical tangent case. So, let us see some examples how these critical cases are coming up and they are covered. Suppose you take y equal to mod x, that is our function. So, at x equal to 0, so you know its graph, it looks something like this, y equal to mod x. At the point 0, we cannot find one unique straight line which will touch the curve. Of course, one is x axis, but we could have taken another something like this, and there are so many, infinitely many straight lines we can draw which are touching the curve at x equal to 0. So, since uniqueness breaks down, we would say that it does not have a tangent. Tangent should be unique straight line. So, there are more than one straight lines that touches the curve at x equal to 0, and so we say that it does not have a tangent at x equal to 0. Let us consider the second example. Here we have the curve as y equal to f of x, which is x to the power 1 by 3. So, look at the point say x equal to 0, that is the origin. This is a point on the curve. So, at that point our definition would say that y axis is a tangent to the curve, because if you change the slope slightly, it will intersect the curve in at least 2 points, and it only touches the curve at 0, not at other points, though in the picture you can't see it because they are too close. So, that is how it goes. There is, we would say that it has a vertical tangent, that is the y axis is a tangent to the curve. But here you see the tangent itself intersects the curve. If you look at some upper side, it is touching, downside also it is touching, and if you vary the slope a little bit, it will cross in 2 points. So, it satisfies our notion of the tangent, that it has only one point common with this, and it is a unique straight line that happens. Other straight lines will not have that property, they will cross the curve at 2 points or even may not cross or may not have a common point with the curve. So, this is a tangent. Okay. So, this is one type of thing, but here there is something else happens. If you take the derivative of this function, it does not exist at 0. Why? The derivative will be f of 0 plus h, which is h to the power 1 by 3 minus f of 0, which is 0, divided by h. So, that gives h to the power minus 2 by 3, whose limit does not exist. In fact, it is equal to infinity, it blows up when h is 0 plus, let us say 0 minus also it is square. So, that would give infinity again. So, once it is infinity, the slope is infinity, it says that there is a vertical tangent, but it does not give us the tangent because it is not differentiable. Okay? Intuitively it says that there is a vertical tangent because it is limit is infinity. So, we will have another example, let us say y equal to x to the power 2 by 3. So, that looks like this, there is a cusp here, it comes down to this and then goes up. It is not like the second one, not like the y equal to mod x, but there is a cusp type of thing. So, what happens here? When you take the derivative, try to compute its derivative at 0, it is h to the power 2 by 3, this is f of 0 plus h minus f of 0 divided by h, that is h to the power minus 1 by 3. When h is positive, it would give the limit as infinity. When the left side limit you take, h goes to 0 from the negative side, you would get minus infinity. So, again the other side will become minus infinity and the infinity. So, you won't get a differentiable, curve is not differentiable at x equal to 0, right. But then what about the tangent? Again you may say vertical tangent exists, but it is not differentiable at x equal to 0, there is a cusp. Okay. But how do you say vertical tangent exists or not? In order to have the vertical tangent exists, we should have the slope as infinity or minus infinity, one of them, but it does not have a limit. So, we cannot say that this y axis becomes a tangent to the curve, right. So, you would say that the curve does not even have a vertical tangent. Fine. So, these are typical examples where there will be difference between the derivative and the tangent, the slope of the tangent which should be the derivative. So, there is a difference. Okay. Now, we will have another thing for the differentiability, this will also figure out in this discussion about tangents. So, what it says, if y equal to f of x is differentiable at x equal to c, then the same function y equal to f of x is continuous at that point. That is what you say this way, if a function is differentiable at a point, then it is continuous. Of course, we can prove it very easily. So, let us say it is differentiable at a point, it is not an end point, but it is an interior point of the domain of f x. Let us take this case. So, in this case we will have the limit of the increment in y divided by increment in x, as that increment of x goes to 0 exists. That is your f prime c here, suppose that exists. Now, it is differentiable at x equal to c. So, that means this limit exists and which we write as f prime of c, f of c plus h minus f c divided by h, as limit h goes to 0 exists. Now, what do we do? We express, because we want continuity. So, let us express f of c plus h minus f of c, that is equal to, forget about the limit now, it is just the expression f of c plus h minus f of c is f of c plus h minus f c divided by h times h. Now, when you take the limit on the left side and also limit on the right one of the equality sign, you see that limit of first expression exists, limit of the second expression also exists. So, limit of the product will be product of the limits. The first one gives f prime c, second one gives 0, that is why it is equal to 0, right. So, what we get is limit of h goes to 0, f of c plus h minus f of c is equal to 0, and that is the definition of, that satisfies the definition of continuity. Therefore, at c f is continuous. So, if it is left or right side only, then also similar things, only one sided limits will come here and you would get the same result. Okay. So, all that we see that differentiability at a point implies continuity at a point. Now, if you take stock, we have this one going along with the tangent. So, when you say something is not differentiable, it can happen from the tangent side if you see geometrically, and also this condition that not continuous also helps. So, these are the cases when a function is not differentiable at x equal to c. What happens? There will be a corner at the curve at that point c f c. If you look at the curve, it happens like in your mod x, y equal to mod x. There is a corner on the curve at that point, say on the mod x, x at 0, there is a corner. Or there can be cusp like your earlier x to the power 2 by 3. So, there what you get? Something like a cusp, which is this case. There can be corner, first case, or this can be second case. There can be a cusp, as we have seen there. Or there can be a vertical tangent to the curve like x to the power 1 by 3, as we have seen here in the third one. Or this condition that the function is not continuous at x equal to c. So, when it is not continuous, it can have some two types of things. There is a jump, that the limit does not exist, right. Limit of the function x goes to c does not exist. Here left side limit is different from the right side limit. Or it can happen that the limit exists, left side limit, right side limit equal to something, some real number, but that is not the functional value. So, it is illustrated in this case. These are the 5 possibilities that can happen when a function is not differentiable at a point. Looking at the geometries. Okay. But what happens? There is something more that will be coming. It is not differentiable, we know it can have jump discontinuity, it can have corners, it can have cusps and so on. So, what our result does not say is that if the function is differentiable at a point, right, then that derivative is continuous. Our theorem does not say this. The derivative can be f prime of x. This function f prime x, the new function, need not be continuous at that point. All that the theorem says that f of x is continuous at that point when f prime c exists. Only that much it says. Okay. So, this is something else, that the new function is continuous or not. So, we can have examples for that. So, let us see the function f of x equal to x square into sin 1 by x if x is not equal to 0 and 0 if x equal to 0. So, it is not differentiable at x equal to 0, or is it differentiable at x equal to 0? Okay. So, the thing is, we have seen this earlier, we have found that at 0, because this is sin 1 by x plus h and so on, if you take x square, so that dominates and that gives rise to 1 x cancels, this gives rise to 0 and the functional value is 0. So, we will show that it is differentiable, but then what about the derivative, the new function? When x is not equal to 0, you will discover shortly, we have not done this yet, how to differentiate this product. It is a product of two functions. We know only for x square, we know only for sine. So, using that we will find out soon that it is, or maybe in the next lecture, that the derivative will be this one, 2x sin 1 by x minus cosine of 1 by x, if it is not 0. That is how the derivative will look like. Now, but you say, you see that this new function, which is f prime x, which I write it as g x, this limit at x goes to 0 does not exist. Why is it so? Of course, this is 2x sin 1 by x, as x goes to 0, sin 1 by x will be bounded by 1 and minus 1, x goes to 0. So, this will give 0, but this factor cos of 1 by x, as x goes to 0, will not exist, right. There can be this 1 by x can take different types of values going up to infinity, right. 1 by x limit goes to infinity. So, near infinity, that is in a neighborhood of infinity, you can find points so that cosine will become 0. You can find also points where cosine becomes 1 by taking suitable multiples of pi or pi by 2. So, you will see that limit g x does not exist, not even infinity or minus infinity, it does not exist, and also neither infinity nor minus infinity. So, you see that the g x or the f prime x, that limit does not exist. So, it is not continuous at x equal to 0, right, but f is continuous. That is what our theorem says, because it is differentiable at 0, f is continuous, and that is also clear. Okay. But there is something else which satisfies for this derivative, that is for f prime x. You remember that if a function is continuous on an interval, then it satisfies the conclusion of intermediate value theorem. That is, if you take an interval a and b, closed interval, where it is continuous, then between f of a and f of b, you take any value, that is achieved. That is, there is one x or c such that f of c will be equal to that value, which is in between f and f b. This is your intermediate value property or conclusion of intermediate value theorem. So, if it is a derivative like your g x here, f prime x, that satisfies this property, right, though it is not continuous, but this is satisfied. So, that is our theorem, that it does not have jump discontinuity. There will not be a jump in f prime x, though that is not continuous, right. We will not prove that theorem, it will again require our completeness property and so on, but we will see that let f be differential function whose domain includes an interval. That is important here, because we want conclusion of IVT to hold. If d is between f prime a and f prime b, then there exists a point c in a b such that this d is achieved, that is d is equal to f prime of c. So, this is what a nice property of derivatives. So, sometimes we will be using this, that otherwise we say the derivative does not have jump discontinuity. That is what it means.